Looking at my last videos, it's not clear what I'm building. The title says sand table, but where is the sand? A while back, I saw a video of one of these, a kinetic sand art table. And these are awesome, but not $10,000 awesome. So I'm going to make my own. For my table, it needs to look just as good and perform just as well as the professional tables you might see online, while costing a fraction of the price. The concept of the table is simple. Some mechanism hidden inside the tabletop moves around a magnet, which pulls the ball bearing through the sand on top. But how do I actually move the magnet? Making a square table would be easy. I could just copy and paste the XY parts of a 3D printer or CNC machine onto the table and call it a day. But squares are boring, which means I have to find a mechanism that fits cleanly into a circle. Normally, we use the Cartesian coordinate system when plotting points, but for this project, I need to use the polar coordinate system. If you plot a point on a plane using Cartesian coordinates, you would write the point as distance on the x-axis, comma, distance on the y-axis, which is very intuitive. But in order to write the same point using polar coordinates, you use the distance from the origin that the point is, as well as the angle from the x-axis. This graph uses radians to mark the angles, but it works just as well with degrees. So in the context of the table, I need to have an axis that spans the diameter of the table and a way to rotate that axis. I opened Onshape and came up with this design. It featured a long rail with a lead screw to move a slider linearly, and a motor underneath to spin the whole contraption. But this was way too over-engineered, and the bottom motor would actually need to be 30 times stronger than it was. So I went back to the drawing board and came up with this design that uses a similar rail and slider, but it was belt driven and it has an off-center theta motor. Not only was this design simpler, but it is cheaper and more compact. Having the theta motor belt driven allowed for massive gear reduction, so there is no doubt about insufficient torque. And instead of mounting the other motor to the rail, it now sits in the middle of the table. In case you're wondering, the motors are NEMA 17 stepper motors, and the belt is a GT2 timing belt, which just so happens to be the exact combination used by 99% of 3D printers, mine included. To power the motors, and to tell them what to do, I'm using an ESP32 S3 dev kit board, which sends commands to two different TMC 2209 stepper motor drivers, which connect to the motor. The TMC 2209 is great because it uses Stealth Chop to make the motor whisper quiet, Stall Guard to feel when the motor hits the end, and the UART serial interface, enabling better communication and control from the ESP32. Also from UART comes microstepping up to 1/256th of a step. Keep in mind that one step is 1.8 degrees, or 200 steps for a full rotation. So I can step the motor 0.007 degrees at a time. So that's what I'm building. In an upcoming video, I'll explain how the software will calculate and control the motors to create those stunning patterns I'm looking for.